All right, I think we'll start. So, Pwn 3, ROP. If you didn't attend like the previous two Pwn meetings, it might be a little confusing, but they're like the meeting slides are still up for fall 2025, and you can just take a look at those. They're actually very comprehensive. Like if you're doing CTF challenges, you can have the slides up side by side. Um, so a few announcements is that LACTF 2026 is tomorrow at 7:45 p.m. We might have hot chocolate, no promises, but we also will probably have pizza, right? So this is going to be like one of our first CTFs of the year, so we're gonna win. There's some IDA Pro licenses on the line, so we can see if we can get one of those. And it's going to be in Siebel CS2406. Um, So here's the meeting flag for Pony CTF. Um, Binary exploitation, in comparison to web exploitation, no offense, um, is a lot more tedious. It's a lot more grunt work, right? Um, but I find it a lot of fun, right? It's a combination of like Rev and other security, like it's binary exploitation, right? It's yeah. So to just review from like Pwn 1 and Pwn 2, here's like the general Linux memory layout. So up here you'll generally have like your lower addresses where you'll have like the actual code that your executable is running. Um, and this is like its data and then globals. And then down here is like where we store the stack in the heap. And if you remember that the heap grows down while the heap or sorry, the heap grows down while the stacker grows up from higher memory addresses to lower, while the heap goes from lower to higher. Um, yeah. So buffers and variables are stored on the stack at a fixed size and like the contiguous memory at the higher addresses. Um, and so like there's specific unsafe functions that can write more data than a buffer can store, leading to buffer overflow vulnerabilities. Like you'll see like common like puts and gets, right? Because you're just able to overwrite the length of a buffer. And we can control the program flow by just overwriting the return address, which is stored on the stack, right? And so traditionally, we would have like a ret to win challenge where you'd essentially allocate like a buffer, and then we allow the user to put like their own input into that buffer. So because the user controls like the length of the string that they put into said buffer, you can actually go above 32 characters and actually overwrite other parts of the stack, right? So here you can see like this would be like the stack, right? Your buffer is on the stack. And if you write more than 32 characters, you're gonna have like you're gonna hit like different parts of the stack, and eventually you'll get down to the return address, which is what we want to overwrite. So for example, here, if we the program will prompt us, right, for like what we want to say, and if we just put like the string a, and then after that, right, if we have like a for 32 characters, and then after that we put some arbitrary address, say like the win function, right, because this will print the flag, we can actually overwrite the return address with our buffer, right? So essentially, you will append to this AAA to get to the end of the buffer, and then after that, you'll append the address of win. You'll have to do a thing called like packing for it because you won't be able to just put the physical number there because of like endianness. Um, but you'll have control over this address, and you have to like craft a payload in order to get to this address, to get to this function, sorry. Because when vuln returns, it will go to this address, and then it will jump here and then print the flag. Um, Another challenge, right, would be like ret to shellcode. So essentially, you can imagine that we have our own buffer, and we can also like control like the padding between our buffer and the return address or anywhere in between, right? We can just control everything after our buffer essentially. So you can imagine that if we put some shell code, we can actually, with an executable stack, execute that shell code by pointing our return address to the start of that shell code. If you don't know what shell code is, you might want to like review Pwn 1 or Pwn 2. But yeah, we can essentially have our own shell code and then have a little bit of padding, and then we'll be able to point directly to the address of our buffer, which you'll usually get through debugging. You'll be able to point that back to our own buffer, and you remember that in our buffer, we just stored a little bit of shell code in there. So then we jump to that shell code, and it gets executed. But a major downfall or major like downside of this is that this is on the stack. And modern executables have a protection called NX. So usually your stack, like with these protections, will only be readable and executable, but will never be writable and executable. So this is like just a new or like a lot of Pwn challenges will have NX enabled. And if you don't, you can use the old methods, right? You can just jump to your own shell code using the return address. But with NX, we have to think of a new method in order to actually execute this code. So we also have the text section, remember? So that was our own binaries code, right? And that's actually executable, if you remember the memory diagram. So because we can't write to the stack anymore and execute it, we can think that, okay, what can we actually be executing? So this leads us to a technique called ROP, right? So the answer to like how we actually get around this is just reusing existing code that is in an executable section, right? And this is like the whole sort of like idea around ROP. So we can piece together bytes that refer to specific parts in an existing executable section of the running program, and then have that chain together in order to achieve functionality that is like akin to shellcode, right? So there's little things called gadgets, and these are the actual pieces of code that you want to find in an executable part of a binary. And if we find those, we can piece them together and execute specific like assembly instructions arbitrarily, right? And usually these gadgets will have to end in a ret instruction so that it pops the next variable off the stack, right? And yeah, these are already on the stack, or sorry, these are already in .text, so these are executable. Yeah, so just a high level overview of ROP. So if we want to get to b=3, how do you guys think that we would go about doing that? Does anyone want to? I'll give you like a minute or two to look at this. So what's like can you give me a series of gadgets, right? You can reuse gadgets as well. Can you give me a series of gadgets that would lead b to be equal to 3 here? Yes.
You start the gadget to the initialize then you repeat gadget one twice, and then you use gadget.
Yeah, exactly. Right. So yeah, we call gadget 2. So this just initializes a to equal 0. And then we call gadget 1, which just increments a by 1 3 times. So it goes a is equal to 0, 1, 2, and then 3. And then gadget 3 swaps a and b, right? So this is just like a high level overview, but then in practice, right, you'll actually have assembly instructions these are like stored in your .text section, and then you'll usually find this through like GEDRA and static analysis. So essentially, I'll explain these gadgets here, and then you can try building another ROP chain from that, is what we call them. So for instance, this one just swaps REX and RBX, and these are registers in your CPU. You can think of these as like temporary variables, right? Sort of like how we have A and B. You can consider like REX and RBX to be their own variables. And then we have XOR RBX with RBX, and that essentially If you take CS233, you'll learn that this just zeroes out a register. So this will set RBX to equal 0. And then the next gadget, we'll just increment REX by 1. And then the last gadget, gadget 4, will subtract RBX from RAX. So can you guys think of, like, for instance, if we were to just ignore this return operation, how do we stack these on top of each other? We can reuse them, right? In order to get to RBX specifically being 3. Does anyone know? Yeah.
Back up RAX and then swap.
Yes. Yeah. Yeah, and then after we swap,
Then, then you have 3.
I'm sorry. So like what? So like all right. So yeah, we swap RX with RBX, right? So essentially, what we have to do first is we have to get RBX to be equal to 0, right? And then we want to swap because we notice that this right here, will actually increment REX specifically. So we want to put that 0 inside of REX. And then we call this gadget 3 times to increment REX to 1, 2, then 3. And then we will actually want to swap it again. So that's an RBX, right? So I think that's what you're kind of trying to.
I left out the initialization.
Yeah, so you have to initialize it because it could be any arbitrary value right now. Like if we just start the execution, REX could contain any value. So yeah, essentially we just set it to 0, swap, and then add 3, and then swap again. And so this kind of thinking, like finding these gadgets in your code and then trying to chain them together, it requires a lot of thought. But there are tools to actually build this sort of chain for you. We'll get to that a little bit later. So essentially, this creates a new exploit if we have a buffer overflow. As you remember, this is stored on the stack, right, which is no longer executable due to NX protections. So what we can actually do is that just fill in the entire buffer, and all 32 characters of it. And then after that, we can put the gadget or the address of our first gadget, our second gadget, and third gadget. Or we could actually just repeat gadgets too. Like we can call gadget 1 3 times, right? For instance. The reason why this works is specifically because returning from this function will actually pop the next value off the stack, which allows us to chain this together. Because imagine in our buffer, right? We have the address to gadget 3, we return, and then we pop the next value off the stack, which let's say that was the address to gadget 1. So now the instruction pointer will go to gadget 1 and we'll execute this, and then it'll keep going back, and that's how we chain these together. You can actually think that if, for instance, our function or like our function that we have to call or like a gadget needs specific arguments, right? We actually need to put things into registers. So if you I don't think 233 covers calling conventions. I haven't finished it yet, but there's in x86-64, actually no, in x86 in this instance, we'll put RDI, RSI, RDX, RCX, R8, and R9. These are the order that you'll have arguments and functions, right? So for instance, void when int a, this would mean that if we actually wanted to call the win function, it would require us to put the whatever value that we want to pass to win inside of the register RDI, because these are like the argument registers. And for instance, our second function will put RSI in there. And this is like covered in Pwn 2, where like you kind of use the arguments, or sorry, you use these registers that you can actually print them. You can print these registers using printf. If there's like a printf vulnerability, and this is actually commonly used to get like stack leaks or like address leaks, because perhaps like an address was stored in one of these registers. So essentially, what if we find a gadget that can set these registers to whatever arbitrary value that we want? So the pop instruction will actually so we can have the address of our first gadget, and then after that we want to put the data that we want to pass. Like this has to be aligned to your current stack, which we'll show you a little bit later. But you put, like, for instance, if we want the first value, like we'll put this also on the stack, and what pop will do is it will pop the next address off of the stack, right? So here we go to this function, and then we use pop RDI, which essentially pops this off of the stack and then puts it into RDI. And that is the first argument. So then we can get the address of when, and then we put that right out under the function argu or sorry, right under the function arguments. And then we are just we jump to it because it's we'll return and then pop the next value off the stack, which because this was already popped, it will be win, and then they'll call win with RDI set to that value, and that will print the flag. So in practice, you usually won't have a win function. So like as you can see here, we can use like a Ghidra to get the address of win, and then we can just put that onto the we can overflow our buffer with that address to go there after setting up the our registers to call that function. So we most of the time in pwn challenges, you'll have to actually pop open a shell. Um, so in order to do that, libc has or like you can either manually do the syscall, but libc has a function called execv, and you can use this to essentially pop open a shell, and you can see that these have quite a bit of arguments. System has less, but if you want to call execv, you'd have to push to your registers RDI, and then RSI, and then RDX, bin, SH, and then 00, or you can just call system. So in practice, right, we're finding and ordering gadgets. Remember how I said that it was actually a little challenging, right? It requires a lot of brain power. Well, actually, like, sometimes you'll have to manually create a ROP chain, but for x86 challenges, for the most part, you can use ROP gadget or one gadget. These are great tools. So ROP gadget will just list all of the gadgets for you, and then you can use that to build your own chain, right? It will like list like the functions that end with ret, right? Um, and you'll be able to like curate through those. You can also use one gadget, which will just give you a ROP chain that will just well actually it will just give you a single gadget to use that will pop open a shell, right? And then you can use pwn tools and pwn debug, and those will help you find ROP chains to use. Um, if you're really up for it, right? I think Sam, he actually was doing a CTF challenge, and they were using a different architecture that wasn't x86. So they didn't actually have any. He didn't have any tools to use like ROP gadget or one gadget for that. So he actually had to go and disassemble it and find the gadgets himself and build the ROP chain. So you might have to actually just do a little manual grunt work if you're using like if there's a different architecture that's being used. So libc, usually we won't have a lot of gadgets in our own. Like imagine you just have like a small binary that's just like has a buffer overflow exploit in it, and then that's it. It's a very small binary. You're not really going to have gadgets inside of that binary. So most of them will dynamically link libc, which gets loaded into memory. And again, that section because will be executable. So we can actually grab addresses from libc and build a ROP chain using the libc addresses while it's like in memory. So these will again like usually be at higher addresses. So if you get a like a leak, you'll usually be able to see if something is a libc address by checking if it's like usually starts with 7FF or like some higher address. Um, yeah. So often the goal is to just leak a libc address because like, sometimes if you have ASLR, the location of libc will actually get randomized in memory. So you'll have to get a leak to it to find the libc base address, and then yeah, so you want to find a leak, and then you want to find the offset from that libc leak. You want to find like an address in libc, then find the offset from that to the libc base, so then you can arbitrarily go to any address in libc. Usually a lot of challenges, they may or may not give you the actual libc. So if they give you the libc, you can just put that into the libc database, and that will allow you to, like, if you like do some like if there's a different vulnerability in the executable to actually leak addresses, you can look up specific offsets inside of the libc database. So for instance, if you know that something is like puts and gets, if you have those two leaked addresses, you can calculate their offset and then put that into a libc database, and it'll actually tell you what libc you're using, and these are good for like blind pwn challenges. um, but yeah, you can also just manually disassemble it and then subtract the offset if they give you the libc. So generally, to prevent ROP, like the mitigation against this would be using PIE or a PI. So this essentially like your actual own executable will have like a random address in memory instead of just being statically like what you would find in the bind, or sorry, instead of like being at one place, like one set address during runtime, it'll just be randomized, right? And again, ASLR will like randomize specific regions like your stack and your heap, and it'll like randomize your libc. So that if you have a randomized libc address, you're gonna have to get a leak in order to find the offset to use. And yeah, base addresses change, but with position independent executables, all of like the code is relative to each other. So if you can find the base address of some pi binary, you can find any arbitrary address in it. In memory. So here's an example using pwn tools, right? So in this case, they give us the libc, and you want to get a leak. So for instance, if we have like a printf, and let's say that like the address for puts is stored in RDI, um, that would get, you can use printf to print that out, and you can get that address of the libc function. And if we have ASLR, we want to actually find the base address of libc in memory. So essentially, if you think about it, right, the actual um, your libc for like the specific function that you know. So like say you have puts, right? Um, the actual libc base address is equal to whatever that real address that you, or sorry, whatever in-memory address that you got leaked, minus the offset from the libc base. Um, yeah, sorry. Minus offset. Oh, I guess I don't know where they're getting offset from here, but generally, your libc base address is like your libc leak minus the actual offset from the libc base of your function. Sometimes there might be an alignment issue, and you'll just have to subtract an offset. I guess that's what that's for, right? Um, so now you can use generally sorry, pwn, you can use pwn tools to they have like a utility to find ROP gadgets. But usually you'll probably want to try using one gadget first. Um, but so you can manually query 4 gadgets in a binary using pwn tools. So in this case, we pop RDI. So we just put whatever's next on the stack into RDI, and then plus the libc address. Uh, and essentially, yeah, so we'll return. Okay, so this is, yeah, this just finds a return gadget, and then system plus libc. All right, so essentially we find using our libc leak, we calculate, or pwn tools will automatically calculate, it'll find the address of system, and you'll be able to craft your payload. And so this is just for stack alignment. Oh yeah, sorry, this is a gadget in order to align your stack to 16 bytes. And then you pop RDI, so put the argument bin sh into RDI. and then we call system, which is in libc with that. So essentially, stack alignment, and then put the address into RDI for the system function argument, which is just yeah, sorry, we put bin sh into RDI, which is the argument to system, and then we actually call system, and then this will pop open a shell. And so further reading, like there's a thing called the shadow stack, and you essentially keep another read-only copy of the stack in a hardware register and compare. And this is another mitigation against ROP and SIG return oriented programming using signal handlers to set registers is an alternative to using ROP and like a lot of modern binaries. There's actually a few challenges that we had on UAU-CTF that uses SROP. Sorry. I don't know how do you close that?
Like guys,
Yeah, okay.
no, use the mouse.
Oh. Okay. And so like if you generally a lot of challenges we use like older libc versions. So you'll be able to use ROP still. So here's some resources. Pwn Tools give you, or sorry, Pwn Tools gives you a lot of like high-level abstractions for crafting exploits for your binaries. Pwn Debug just gives you like it gives you more information at every single like breakpoint than like GDB would, which is useful for like binary exploitation. ROP gadget to find the specific gadgets given a binary. One gadget to just if your libc has like one gadget in it, you can just try using your ROP chain set to that and see if it pops open a shell. Otherwise, you might have to manually create your own ROP chain. And then the libc database search, which we can use for blind pwn challenges if they don't give us a libc, or you can just disassemble it if you are given your libc. And then the ROP Emporium is like just a bunch of practice problems that you can use. Yeah. And so next meetings, there's no meeting this Sunday. That's canceled. It's going to be the Super Bowl. And then next Thursday, we're going to do esoteric languages. So we'll learn a bunch of SO langs and how to rev them. Yeah. And here's the meeting flag again.